Good evening to everyone. As I was introduced, my name is Vasilios. I was the mechanical engineer on this project, responsible for the energy modelling component. With regards to this presentation tonight, I will break it up into three parts. The first part will discuss the methodology with regards to the energy modelling. Second, I will discuss the definition of the problem, and thirdly, I will review the solutions that we found through the energy modelling. I mean, the first thing that we sought to do was quantifying how severe the problem was, and we could have done that via two ways, and one would have been to actually go and measure the building's performance during summertime, which was not practical. We didn't have data, it would have taken too long. And the second solution was obviously to do the energy simulation via Design Builder software. The reasons why we use Design Builder for our energy modeling is because it has a graphical interface and it's quite easy to construct a three-dimensional model of the building. It can simulate 8,760 hours per year, so it simulates for every hour of the year. And in addition to that, the software is best tested and certified by the US Department of Energy. So we're confident that the results that we would be getting would be quite realistic. The first step in the energy modelling process was to construct the model geometrically. Then we entered the building fabric construction, and that included the roof structure, which was just a plain metal roof, the wall structure, which was just a simple double brick construction, and the windows and openings. In addition, we added the occupancy numbers and the number of people within the building, the operating schedules, and equipment that consumed lighting and power. And that was important because lighting and power equipment, they emit heat and increase the building's internal heat gain. With regards to the problem that we were engaged to solve, the client had complained that during a hot summer day of 30 degrees inside, it was also hot, it was 30 degrees, and workers had to could only work in half-hour shifts and then take a rest for half an hour. So the building was very hot, and the productivity inside the building was quite low. Here is a small sample of what the model looked like in the simulation. Let me also show you a sun path diagram of the same building within the model, which depicts how the sun's radiation impinges onto the building structure. So, following the construction of the building, the results were quite interesting, and they showed that for a 30-degree summer day, the indoor temperature would rise to 38 degrees. So this happened around 4 p.m. In addition, in the morning at 8 a.m. when outside the temperature was 25 degrees, inside when the workers would start work, the model showed that the temperature was 33 degrees Celsius. So what the model clearly showed us was that the building was operating like a heat oven, which stored thermal mass from the sun within within the building fabric walls. So all day you'd have the heat from the sun and the solar radiation hitting the metal roof, and then that would be transmitted into the walls and the concrete slab and the floor of the building, and it would be stored there. So that's why you'd have these very high above ambient temperatures. So on an average 30-degree day, we saw that the indoor temperature was about 8 degrees higher than the outdoor temperature. So following the construction of the base building, the original building, we played around with a couple of options. And the first option that we looked at was increasing the roof insulation to an R value of 3.2 as part of our building fabric recommendations. We also looked at the effect of adding heat reflective paint, and the results showed that although it did have a significant effect in cutting out the heat during summertime, but because of the thermal mass and the high internal gains, and as we discussed before, the internal gains were from two components, and one was the indoor equipment and the lights, and the other one was the occupancy and the people. Because there was heat gains from those two components, just using the roof insulation would not be sufficient enough to cool down the building. So workers would still, the model showed that workers would still walk into the building in the morning and be quite hot. Then we sort of played around with the idea of introducing roof ventilators. So we've simulated the building with the new roof insulation, which had an R value of 3.2, and we simulated increased ventilation rates to see what effect that would have in the internal temperature. So from trial and error, we found that the optimal ventilation rate for the building would be 5.2 air changes per hour. And the results show that at 5.2 air changes per hour, if we ran the fans for 24 hours on a 30-degree day, we would get an internal temperature of 31.6 degrees. Then we had a look at different types of operating schedules for the ventilation, and we experimented with 8 hours of ventilation per day as opposed to 24 to see if we could save energy and what effect this would have in the internal temperature. So at 8 hours we found that the internal temperature was 32.6 degrees. And the difference was not very significant. Obviously you would have more of a lower temperature. The temperature would be reduced at a 24-hour operation, but sometimes it's not cost effective to do so. So therefore we established through the energy modelling that by insulating the roof and by introducing an optimal ventilation rate and by introducing this ventilation for 8 to practically say 10 hours a day, that would be sufficient enough to cool the building by 5 degrees compared to the existing building. The insulation also had significant effects on the heating as well and wintertime performance. With a standard building during wintertime, for an 8-degree outdoor temperature, the energy model showed that the indoor temperature would be 9.6 degrees. The insulation would slightly increase this, so you'd have an 11.2 degrees indoor temperature compared to a 9.6, which is 1.6 degrees higher. In addition, for winter-time performance, we also looked at the effect of adding heat-reflective paint onto the roof and what effect this will have in the internal temperature during wintertime. We found that there's no significant loss of temperature during wintertime. So the recommendations that we made to the client were insulate the roof to an R value of 3.2, paint the roof with low E heat reflective paint, introduce mechanically assisted ventilation at the rate of 5.2 air changes per hour and operate for 8 to 10 hours a day. And with these recommendations, the model showed that the effects on thermal comfort for both winter and summertime would be greatly improved. Thank you.